A number sequence is a sequence of numbers in order. For example, if you have a number 1, number 2, 3, and so on. And they could be finite or infinite. Normally we will look at infinite. So for example, if you have the odd numbers, you have 1, 3, 5, 7, and so on. Or either prime numbers, 2, 3, 5, 7, 11, 13, and so on. So these are examples of number sequences. You can give a number sequence also, for example, with an explicit formula. For example, the nth odd number can be given by this formula. So if you put n equal to 1, 2 times 1 minus 1 is 1, and then put 2, then we have 2 times 2 is 4 minus 1 that's 3. So you get all the odd numbers just plugging into this explicit formula. So you have 01, 02, 03, and this is 1, 3, 5, and so on. So that's an explicit formula giving you the number sequence. Then you also could have a recursive formula. And that only gives you the number sequence implicitly. For example, the odd numbers could also be given by this recursive formula. So if you have the odd number n, you get the next one just adding 2. So if you start at 1, then the next one in line will be 2 more. So you see here, for example, that odd number 2, that's odd number 1 plus 2. So this is 1 plus 2, 3. And odd number 3, that is odd number 2 plus 2. And now we saw that odd number 2 is 3. So this 3 plus 2, 5, and so on. So this is called a recursive formula. And then we have to have some starting value here. So we start with odd number 1, and then the rest is given in terms of the next one. Then you can also visualize number sequence with, for example, figurative numbers. And those we have already come across before. For example, the triangle numbers. Those are, the first one is you have 1. And then the next one, you put them in a triangle like this. So then you have 3. Then the next one, so you make up these triangles. This is 5 balls. And so on. So here we get this number sequence 1, 3, 5, 9. This sequence is called a triangle of numbers because you can visualize it like this with triangles of balls, for example. Then you can have the square numbers and other figurative numbers. An explicit formula for triangle numbers, for example, this is T1, this is T2, T3, T4. So the explicit formula for those, for example, the nth triangular number, you can just add, so 1 plus 2 plus 3. Since you see you have 1, then you have 2, 3. So you just add them up like this until you come to the nth. However, this is not a very, it can be very long explicit formula, but you can also show that you can also write this as this. So it can be shown that this long sum can be written as this. So this is an explicit formula for the triangular numbers. An arithmetic progression, that's a number sequence where the difference between two numbers is constant. So you have that if you have the nth plus 1 number and take away the previous number, am, this is a constant. And that constant can be any number. For example, the odd numbers are arithmetic progression. For example, if you take the nth odd number and take away the previous one, that's 2. So 2 consecutive odd numbers, they differ by 2. So that's an example of this. And also the even numbers differ by 2 for 2 consecutive numbers. This is also an example of this. And then you have a geometric progression. And then you have that the quotient between 2 consecutive numbers is a constant. So if you have the nth plus 1 number and you divide by the previous number, then that's a constant. For example, the sequence 1, 2, 4, 8, 16, 32, and so on. You double each number. That's an example of geometric progression. Because here you have, for example, take this divided by that is 2 divided by 1, that's 2. Or 8 divided by 4, that's also 2. 32 divided by 16, and so on. So you take 2 consecutive numbers, then the quotient will always be 2. So that's an example of a geometric progression. So let's look at the following number sequence, and we write our theorem. So if you have a geometric progression, and you add all the numbers, so then you get this sum. So let's call this sum here. So 1 plus a squared plus. So here a is some number. So you add all the numbers up to am. If you would treat this as a sequence, so 1a, a2, a3, and so on. This is an example of a geometric progression, because each number is, you get the next one multiplying by a, or you get, take this one divided by the previous one, you get a for all. So that's a geometric progression. So if you add all those up in the number sequence, then you get this sum. And this sum, you can show that this sum is given by the following explicit formula. So take am plus 1 minus 1 divided by a minus 1. Okay, so that's the theorem. We will prove this, but let's first take an example. So say that you want to calculate this sum. So you take the sum of a geometric progression. So this is sum of numbers you double. Okay, so let's say you want to take, you want to calculate this sum. So this is the same as 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, and so on, until you come to this one. And 2024, that's 2 to the raised to the power 10. So we want to calculate this sum. So let's call this sum for S10. This is the sum here. So it's, in this case we have that a is equal to 1. A is equal to 2. So this is an example of this, but a is equal to 2. Then we have, according to this formula here, that S10 is equal to A11, so 1 more than this, minus 1, A minus 1. And here A is 2, it's 2 to 11, 2 minus 1. And this is double this, so this 2048 minus 1 divided by 1. So it's 2047. So if you add this sum here, that's 2047. And that you can find out by using this explicit rule. Now we will prove the theorem, that is, that this sum here is given by this explicit formula. Okay, so let's just write down what sum we have is 1 plus a squared, and so on, up to am. If we multiply both sides by a, what do we get then? Okay, if we multiply in here a, then we get a, then a squared, a cubed, and so on. you get this. Okay, let us now take this A times Sm, and subtract Sn. This one is equal to this sum. Okay, and then we subtract Sm, and that's just this sum. And now, if you want to remove the parentheses, then we need to change the signs. But now we see that most things will cancel. So we see, for example, this will cancel to that. This will cancel to that. This will cancel to that. And what is remaining? The only thing that will remain here now is this part. So am plus 1 minus 1. Okay, so we have arrived at this is equal to this. However, the left-hand side here, we can factorize out Sm from there. So this left-hand side we can factorize Sm, and then we get that. And that should be equal to that. And now we can just divide by a minus 1 on both sides. And then we get Sm. And this is just the explicit formula we wanted to prove. So that concludes our proof. A well-known sequence of numbers is the Fibonacci sequence. And then in the Fibonacci sequence, you start with the 1 and the 1. Then the next one is given of the two previous ones. So 1 plus 1 is 2. Then 1 plus 2 is 3. And 2 plus 3 is 5. 3 plus 5 is 8. So this is how you calculate the Fibonacci sequence. 21. In this sequence, you can give it with a recursive formula like this. So if you have Fibonacci number n, that's given by the previous one and the previous to that. So it's given by this recursive formula. And here you need some starting value of the sequence. So f1 equals to f2 equals to 1. So this is a recursive formula giving you this sequence. So if you plug in the first two, so 1 and 1, you get number 3. It's just a sum. So you see that the next one is just given of the two previous ones, sum of those. So this number sequence is named after the Italian mathematician who lived in the 12th century, 12th or 13th century. And he discovered this formula, this sequence, when he studied somewhat idealized rabbits in rabbits population. Okay, so his assumption was that every rabbit couple give birth to a new rabbit couple every month, apart from the first month when they are young. So the number of rabbit pairs on the certain month is then given by the Fibonacci sequence. So you start with one rabbit pair, then the first month they don't do anything according to this model. Then the next one, then you get 2. And then you have a newborn here. This newborn doesn't do anything the first month. This one is not, this is the parents. So this also continues to breed. So here you get a new couple. and then this is newborn, and this is the old one. So you see it continue in this fashion. If you calculate how many rabbits you have after a certain number of months, then it's given by this Fibonacci sequence. First you have 1, 1, 2, then 3, then 5. You see that's the same as here. And the Fibonacci sequence is important not just because of this example, but it comes up in many different contexts. For example, having to do with flowers and seeds and plants, but also in economy. And also, for example, how long time it takes for a computer to calculate the greatest common divisor using Euclid's algorithm. So this number sequence pops up in different contexts.